Every time your program runs an if statement, your CPU guesses the future. It predicts which path your code will take before the condition is even evaluated. In fact, modern CPUs make these guesses billions of times per second, and they're right more than 95% of the time. So, how does this piece of silicon predict the future? Let's explore branch prediction on today's episode of Fully Attributed. CPUs are insanely fast because they don't execute one instruction at a time. They use something called pipelining, where fetching, decoding, and executing happen in parallel. In this program, while the CPU is executing instruction A, it's already decoding instruction B and fetching instruction C. This overlap lets the CPU work on multiple instructions at the same time, instead of waiting for each one to finish. Now consider the if statement. In assembly, it would look something like this. In a pipeline, this becomes a problem. When the CPU is decoding the JLE instruction, it doesn't yet know which instruction comes next. The program counter might continue forward, or it might jump to L1, and that decision won't be ready until the execute stage finishes evaluating the condition. So the entire pipeline has to wait for a cycle to find out which instruction to fetch next. This pause is called a pipeline stall, and on modern CPUs, stalls are really expensive. So how do CPUs deal with this problem? Early processors started with very simple guesses. Strategy 1, assume that the branch is never taken. Strategy 2, assume that the branch is always taken. The key idea here is that the CPU doesn't need to wait for the condition to be evaluated. It immediately starts fetching instructions from the path it thinks will be executed. If the guess is correct, we save about one clock cycle because the pipeline keeps moving forward. If the guess is wrong, the CPU has to flush the pipeline, throw away the incorrectly fetched instruction, and then fetch the correct one in the next cycle. These naïve strategies typically achieve around 50 to 60% accuracy, which was considered acceptable in early designs. After that, CPU designers began looking for patterns in programs. They noticed something very simple. If a branch jumps backward, it's probably just a loop. So take it. Otherwise, don't take it. Think about a loop like this. Loops usually repeat. So when we see a backwards branch, let's predict that it will always be taken. And with this one simple rule, prediction accuracy jumps to around 60 to 70%. But real programs aren't just simple loops, and this is where things get interesting. Modern CPUs don't just guess, they remember. Every branch instruction gets a tiny entry in a table called the branch history table. For each branch, the CPU tracks what happened last time and predicts that the same will happen again. This is called a 1-bit predictor, and it typically achieves around 70 to 80% accuracy. But the problem with the 1-bit predictor is that it flips its prediction too easily. In patterns like nested loops, a single unexpected branch can throw it off. So, CPUs instead use a 2-bit predictor. Instead of storing just 1 bit per branch, the predictor stores 2 bits, which represent 4 states: strongly taken, weakly not taken, and strongly not taken. Let's see how this works. Assume a branch starts in the strongly taken state, so the CPU predicts that it will be taken. If the branch turns out to be not taken, the predictor doesn't flip immediately. It moves to the weakly taken stage. It will still predict taken. If the branch is not taken again, it now moves to the weakly not taken. And only then does the prediction change. So a single wrong guess doesn't reverse the decision. It takes 2 mispredictions in a row to flip the prediction. That small change makes branch prediction far more stable, especially in real noisy programs. In practice, 2-bit predictors reach around 80 to 90% accuracy on typical programs. You can build predictors with even more bits, but beyond 2, the gains are small while the hardware cost keeps increasing, which is why 2-bit predictors became so widely used. But this is just the basics of branch prediction. Modern CPUs don't rely on a single predictor. They use multiple predictors at once: local history, global history, tournament predictors, and so on. In fact, they use predictors that predict which predictor to trust. We'll cover these advanced predictors in another video. Remember, all of this happens in hardware, in less than a square millimeter of silicon. It's one of those details you never see, but your code depends on it every second. Thanks for watching. If you enjoyed this video, hit the like button and subscribe, and I'll see you in another episode of Fully Attributed.